So good morning. I hope you're all doing well today. Very nice morning. Actually, I wish we had a lecture outside. Maybe it's still a little bit too chilly. Maybe in a matter of 2 weeks we could do this. Right? Somewhere in the garage.
Who's going to carry the blackboard?
I don't know. So we'll have to figure something out
Right on the sidewalk.
Or we first record it and then we just watch it there. You know. In some sort of barbecue environment. I know. We can do this. Anyway, good morning. So, as you know, as you remember, we started discussing the many-body perturbation theory as a way to solve the Many-Fermion correlation problem. And to be specific, we started discussing the underlying theory called Rayleigh-Schrödinger perturbation theory for a nondegenerate Hermitian eigenvalue problem. K psi node equals K node psi K node psi node. Okay? Where ultimately, when we're done with the discussion of Rayleigh-Schrödinger perturbation theory as a way to solve this eigenvalue problem, we'll then, in the end, say that our K in our MDPT considerations will be the Hamiltonian in the normal product form, and our K node will be then the correlation energy, the difference between the energy of state psi node and the expectation value of the Hamiltonian in the unperturbed state phi node, which by essentially our assumption dominates the expansion of psi node in terms of state determinants. But for the time being, we'll be focusing on the more general problem, solve the eigenvalue problem of this form. In perturbation theory, we are assuming that we can split the K operator into the unperturbed part, K node and perturbation in such a way that we can find all eigenstates and all eigenvalues of the unperturbed operator K node. In other words, we know all the eigenstates and eigenvalues, phi n and kappa n respectively, where n goes from 0 to, well, in principle infinity, but of course we can also operate in finite basis sets, then the number will be finite, as big as the size of the Hilbert space. Of course phi 0, our unperturbed state, is among the solutions. That's of course what we are assuming here. Good morning. All right. Of course, our goal is to develop a method where psi 0, our target state, is written as a series which starts with phi 0. This is our unperturbed state, and then various corrections to the wave function. Maybe I'll write it this way. Psi 0 n, where n goes from 1 to infinity. Okay? And of course, we would also like to know the corresponding expansion for the eigenvalue K0. So we're going to start with kappa 0, which is our unperturbed eigenvalue, and then various corrections that in principle should start with the first order. So we have K0n, where n starts from 1 and goes all the way to infinity. So in other words, the zero order approximation to the wave function psi naught is simply phi 0, which is the eigenstate of K0, and then the zero order correction to the eigenvalue K0, 0, ultimately correlation energy, is simply kappa 0, the unperturbed, the eigenvalue of K0 with phi 0. Okay? All right. And as I explained last time, in sort of the modern formulation of perturbation theory, the way you approach this is by introducing the wave operator. So we are trying to transform the unperturbed state phi 0 into the perturbed target state psi naught with the help of the operator omega. And our goal is really to find omega and then find the proper perturbative representation of it with various corrections to it. Okay, and we are, in doing so, we are imposing the intermediate normalization condition that an inner product of phi 0 and psi 0 is 1, which is of course the same as phi 0 inner product with phi 0, and that is of course also the same as phi 0 as the expectation value of omega in phi 0. This is all the same thing written in various ways. Okay, so we know that we'll be imposing a condition on the form of omega through the intermediate normalization. Okay, and then by simple manipulations we demonstrated that with this form of the wave of the eigenstate psi naught, we can write the eigenvalue k naught that corresponds to it as kappa 0 plus an expectation value of an operator tau, which we call the reaction operator, which is actually directly related to omega. Okay, it is W omega. All right. Actually, you will see today that actually we're going to have P here because that will I was initially sort of not entirely precise because we were still in the initial discussion. But you can see that if I put P here, that doesn't change the result because P is the projection operator on phi 0. So obviously you can stick it there, and that's the final formula for the reaction operator. Anyway, since I defined here the P, let me remind you what it is. It is a projection operator on the unperturbed space, right? In our case, the one-dimensional space spanned by the unperturbed state phi 0. And then what we did, so I'm essentially going through our last lecture. Okay, what we did next is we wanted to find a representation of our eigenstate psi naught, our target eigenstate, okay, using the concept of the reduced resolvent, of course, which meant that I had to introduce the reduced resolvent. As you remember, the reduced resolvent was defined as an operator which has the projection operator Q in front, and then we have alpha P plus Q kappa minus K Q to the minus 1 Q. Alright? So in this definition, P is the same projection operator that you see over there. Q is a projection operator on the orthogonal complement of the P space. So it's simply 1 minus P. And then of course you can also write it as the sum of projection operators on individual spaces corresponding to all those phi x other than phi 0. Okay? And so essentially what is reduced resolvent? We analyzed it. It is essentially an inverse of kappa minus k in the Q space. And then we prove properties 1 through 5 of this reduced resolvent. We'll be using them as the need arises. I'm not going to copy them. You have them in your notes. And we can always restore them if necessary. Okay? So we prove properties of the resolvent, and then having all those properties around, what we did is we started, we proposed a sort of a generalized form of the solution of our eigenvalue problem, the one on, at the top blackboard, k psi naught equals k0 psi naught, okay, in the following form, phi 0, which is our unperturbed solution, plus the reduced resolvent, okay. I'm gonna, as I said, I will sometimes write this reduced resolvent without putting k in it, okay. We will always remember that if I don't say anything, r kappa means r kappa of the k operator, okay. So then the definition of this generalized form of psi is phi 0 plus the reduced resolvent at kappa, acting on the k, acting on phi 0. Side, I don't think I need this anymore. And so in other words, we proposed what I think I describe as a trial state or trial function. And with this definition of this trial state, we showed that kappa minus k acting on this trial state gives us kappa minus a new function f kappa times phi 0, where we introduced a function f as phi 0 k psi kappa. Or, if you work it out more explicitly, we know how what psi kappa is. We end up with phi 0. The first term will give us simply k, and then the second term will give us k, reduce resolvent k phi 0. Okay? And I call this function f the bracketing function, and we'll talk some more about it today. But before I do this, I said, I think, last time that this is an amazing equation. Maybe I use another word for it. But anyway, it's a great equation because it's a way, it's a very elegant way of finding actually solutions of the Schrödinger equation. You know, our eigenvalue problem k psi 0 equals k0 psi 0. It's a Schrödinger equation for us, ultimately, because k will be the Hamiltonian. Okay? So if you find fixed points of function f, so in other words, if you solve this equation, you know, plot f as a function of kappa and cross it with a line, all the crossing points will give us eigenvalues that we are looking for. Okay? Because if you do this, then the right hand side becomes 0, and then you end up with kappa minus k psi equals 0, which is exactly the eigenvalue problem we're trying to solve. But I made a comment at the end that we have to be a little bit careful about the formula at least. That is, we cannot find all eigenvalues. It would be great if we could, but we cannot find all eigenvalues of operator k in this way, because you can see our definition assumes that psi has a p-space component, phi 0. So in other words, we cannot find those solutions of the Schrödinger equation ultimately which are completely orthogonal to phi 0, and we cannot find those solutions for which kappa causes a singularity. And we know how this happens if you go back here. If you choose kappa to be an eigenvalue of the projected form of k, that is the one, you know, what I call, I think, kqq, you know, the qkq, k operating within the q space only. If you choose kappa to be an eigenvalue, sorry, I should say maybe if it happens that our eigenvalue of the k operator is also an eigenvalue of the projected operator k, all right? Well, then we cannot find such solutions of the Schrödinger equation, okay, or our eigenvalue problem. And you know, and the easiest way to explain it is, you know, by using symmetry. If you are looking for a state which has a different symmetry, then suppose psi 0 is a ground state, and essentially it's going to be a ground state for us all the time, or the lowest, in principle, the lowest state of a given symmetry, and non-degenerate lowest state of a given symmetry. So if psi 0, if the eigenstate you're looking for is say has a different symmetry than the ground state psi 0 you're looking for, then it will not have a phi 0 component, because phi, you know, the overlap with phi 0 will be 0. Okay, and that means that we will not be able to find such a state in this sort of simple way. We will have to change phi 0, because you know what you do, it's not like you cannot do it at all. You just have to pick up a different phi 0, the one that has a non-zero overlap with your target state. Okay, so that's the only thing. So is this clear to everybody? That, you know, this is a nice trick. This is a nice way to get solutions of the eigenvalue problem we're interested in. Okay, but we have to remember this is not the trick that allows you to get all eigenvalues. Only some of them. Only those eigenvalues and eigenstates. Only those k's and those psi's which those psi's that have a non-zero overlap with your unperturbed state, and those k's which are not eigenvalues of the projected operator k, projected on the Q space. All right. But this is not a problem for us, because in our case, you know, the solution we're interested in is kappa equal k0. That's what we're really looking for. We are, of course, choosing phi 0 to have a non-zero overlap with psi 0. Okay, that was our intermediate normalization condition. So we're not running into the risk that somehow our psi 0 will become orthogonal to phi 0. If that, you know, if that happened, we will have to just change phi 0. Okay. So in this case, we can use this formula, and if kappa is k0, and let me write the formulas that emerge, then we will have K0 minus K acting on the corresponding, I'm going to call it now psi naught, is 0, because at this point we have a situation where f at K0 is K0, and then this means that right away from these general considerations we know how the solution will look like, how the eigenstate psi will look like. Psi, by simply copying from the left blackboard, will be phi0 plus the resolvent of K computed at K0, alright? Then K phi0. And then if you want to know how the eigenvalue will look like, so K0, it is simply the value of the bracketing function at K0. We know what the bracketing function is, we have a definition of it. So right away you have access to the mathematical form of the eigenvalue. It is phi0 K plus K resolvent at K0 K phi0. Okay? So it is sort of a quasi-analytic solution of the Schrödinger equation if K is the Hamiltonian. Okay? Because the procedure then is the following. Calculate the bracketing function f. You know, we have a formula for it. We know our operator K. For every kappa, I know how to calculate the resolvent. I have a formula for it as well. It's all explicit. I plot f. I draw a line. I cross that line with f. Find my eigenvalues. Stick those eigenvalues into the resolvent, and I get my eigenstates. And I'm done. You know, it's a procedure to solve the Schrödinger equation, actually. Alright? I'm going to now show you how this procedure looks like in a specific sort of how it looks like. But before I do this, let me also say that we'll be interested in, of course, in sort of applying these expressions to our wave operator omega. Remember, our target, really, formally speaking, is our wave operator omega. So if you look at this expression, you can see that I can actually give it a form of omega acting on phi0, right? As long as I define omega as, for the phi0 part, I will have a projection operator p, because that doesn't change phi0. And for the q-space component, I will simply have the resolvent k and p here, because p, when you apply it on phi0 here, will produce phi0. Okay? So actually you can see that what is beginning to emerge from these considerations is actually the desired form of the wave operator. Okay? As I said, you know, now you can see this is actually a fully defined, well-defined wave operator. I said in the beginning, wave operator omega was not defined. Because, you know, in the beginning I only said that omega converts phi0 into psi0. Well, that's not the definition of an operator. This is a recipe how to convert phi0 into psi0. Right now we have a full definition of omega. Okay? We know, you know, you have a formula, you can just act with it on any function you want. On any state in the Hilbert space you want, right? In most cases, nothing interesting will come out, but you have a definition. It is now a well-defined operator. And of course, you know, when you look at the K0, since K0 is given by this expression, then immediately we can say that, you know, by simply comparing these equations, you can see what you have here is K multiplying omega. All right? So we have K omega phi0. So you can see that I am beginning to sort of generate expressions that have the desired form. There's a wave operator, okay, and then we're producing the perturbed state out of it, okay, and then the perturbed eigenvalue. But for the time being, what I would like to do, I would like to keep that kappa dependence, okay? It is more elegant this way, more and sort of more, I guess, appropriate at this point. So what I'll do is this: I'll continue considering expressions of this sort, where kappa is still a variable parameter, and when I am done, okay, with perturbative expansion, I will simply say kappa equals K0. So it's going to be a simple substitution at the end, okay? So in this way, we'll retain the mathematical elegance of this and generality. So in other words, what I'll do right now, and you know, maybe I'll actually do it here. I'll come back to the other blackboard, but let me actually, since we don't need all these equations right now, this was a review, so what I'll do, I'll erase most of it, maybe all of it. But I'll write now equations which will be useful for us. That is, maybe, let's see, let's put this one up for a second so you can see the whole thing. Alright, so what I'll do, in analogy to our desired psi0 and k0, I'll say that psi kappa can be generated by the generalized form of the wave operator. I'm going to call it omega kappa, except there's kappa if there's kappa here, okay, acting on phi 0. And from our definition of the trial state, omega kappa is given by the following formula. The projection operator P, just like in the omega case, plus the reduced resolvent computed at kappa, acting on K, and then, you know, multiplying the P, right? So that's what so it is really a similar formula to what you see there, except that now I am retaining this kappa dependence, okay? And then, since we are talking about kappa being still a variable parameter, then the corresponding bracketing function can be written as phi 0 k omega kappa phi 0. Okay? So this is going to be the set of formulas that we'll use. And this, maybe I'll store the equation which is on the upper blackboard, with the one which is in the box. Okay? It's going to be useful to remember about it for us. So, okay, so we know that our psi kappa defined through this generalized form of the wave operator satisfies the equation kappa minus f kappa, okay, times phi 0. Okay, so this is the set of formulas which will form a basis for the Rayleigh-Schrödinger perturbation theory. Okay, now what I would like to do at this point is this all clear? First of all, I realize it's abstract. We're sort of now. I told you we're going to be climbing the hill, maybe a big mountain, right? I'm going to hopefully today reach the top. Okay, and then we'll see the view of what is perturbation theory, big one, right? I just want to make sure that nobody's lost at these considerations. I realize there's lots of manipulations, but is this all clear? That these formulas, how we arrived at them, and more or less what's the meaning of them? Okay? All right. So you can see, to summarize, right now we reach the stage where we have a proposal for how the solutions of the Schrödinger equation should look like. Okay? We'll obtain them using this formula, where kappa will become K0. Okay? Right now we know that we can find K0 by just crossing the line with F. Okay? Alright, that's all we know. We'll find a better way than this. Okay? Through perturbation theory. And then once we have K0, we can spell out the omega, the final omega on the other blackboard, and the final form of the eigenvalue through the bracketing function. Okay? I would like to actually show you the bracketing function now, because there are lots of interesting things about it. But, and we need to sort of maybe explain where the name bracketing function comes from. Before I do this, let me maybe demonstrate the three basic properties of the wave operator omega, which actually, are very important and need to be spelled out here. We can prove almost immediately, as you will see now, that omega kappa, and of course that means that the other omega too, because the other omega is just a special case of omega kappa, okay, satisfies three properties. The first one is P omega kappa equals P. Okay, this may be called the property 1. Right? The second property is that if you apply omega kappa to P, then you end up with omega kappa. Okay? And the third property is that omega kappa squared is omega kappa. So omega is an idempotent operator. Okay? I'll comment on all three in a moment. Before I do this, let me just prove all three. And maybe, since I would like to perhaps keep some of these formulas for some time, what I'll do, I will maybe, let's see, I think I can now erase what's on the top blackboard. I'll move it down. I'll erase what we have here. And I'll prove these three properties first. Of course, if since we know what omega is, the proof is straightforward. If you start with property 1, P omega kappa, you can see what omega kappa is up there. So you end up with P squared plus P reduced resolvent K P. Alright? But, obviously, P acting on the resolvent is, maybe you can tell me what do you think it is? Yes. Do you know why?
Well,
we can explain everyone.
Reduced resolvent only as it is only part.
Yeah, exactly. you know, always have to just remember that one thing, that resolvent, you know, whatever's in the middle, you know, we may always forget, but there's a Q on both sides, right? And that is enough to say that that's a 0. Perfect. Okay? And P squared is P, because P is a projection operator, it's idempotent. So we know with P, and I'm done with property 1. You can see how quickly that goes now. Property 2. Well, that's even easier. Okay? Because now from the definition, we end up with P squared plus the reduced resolvent K P squared. But P squared is P. So we end up with P plus reduced resolvent Kp, which is of course omega kappa, coming back at us. And the third property, you're going to see the fun proof of it right now. Okay, so how do I prove that omega kappa squared is omega kappa? So now, please watch that. It's omega kappa times omega kappa. From property 2, I can replace each omega kappa by omega kappa p times omega kappa, I can replace each omega kappa here by omega kappa p. That's what I'm doing. So here I'm using property 2. Okay? Now I can rearrange the brackets. Okay, so I can write it as omega kappa p, omega kappa p. But we proved in our point 1 here that p omega kappa is p. See the little game I'm playing? It's gonna be omega kappa p squared. But p squared is p. So I end up with omega kappa p. Alright? So here maybe I should say I use property 1. Okay? But through property 2, omega kappa p is omega kappa, and I'm done. You see what I'm doing? Just playing a little game with properties 1 and 2, back and forth, I end up with the desired expression. I think students in high school should be able to do this. Maybe they wouldn't know what omega is, right? But doing that kind of manipulation, that's really at the level of multiplying numbers almost, right? As simple as that. Okay? But it's a very powerful statement. The proof is straightforward. It's a powerful statement. What does it tell us? It tells us that omega, the wave operator, is an idempotent operator. So you can imagine that it does change phi 0 into psi, but it's not going to change psi any further. Okay? Another application of omega to the perturbed state actually will keep it there. So in a way, you can treat it as a projection operator. You know, an operator that doesn't change things, you know, is typically a projection operator, okay, on the space that contains the thing we're trying to apply to, okay? But it is not a projection operator. Some people call it a non-orthogonal projector. Okay, well, all right, we can invent new terms if we like. All right, but it's not a projection operator because projection operator has to satisfy two properties. It has to be idempotent and it has to be Hermitian. Okay, omega, as we define it, is not Hermitian. Let's emphasize this. You can see that it's not Hermitian from the definition of it. Okay, you can see that the p part is Hermitian, so the z unperturbed part of omega is Hermitian. It's just that the perturbation part makes it non-Hermitian. Okay, because if you wanted to take an adjoint of it, you have to read it backwards, right? And obviously that's not gonna, you know, p doesn't commute with the resolvent. So K, I should say, K does not commute with the resolvent. It's far away because, you know, resolvent has the Q space component, you know, the Q and P. Right? So you cannot, you know, you have to keep the order, R, K, P. You cannot write it in any order you like. All right? So it's not Hermitian. So it is an operator that doesn't change psi. In that sense, you know, it is a projection on psi, but it is not Hermitian, so it's not a real projection operator. But of course, you know, I would like you to register that information. The fact that I'm kind of saying that it's some kind of a projection operator, not a real projection operator, but some kind of. Why? Because you can think of alternative theories. Right? We could say, impose the condition that actually omega is Hermitian. All right? We could do this. Then we would, there would be some other advantages. This is not what is done in Rayleigh-Schrödinger perturbation theory, but one could consider other forms of perturbation theory where you impose, say, a condition of Hermiticity. Right? So there are things that one can do beyond what we are doing here, and so I'm not going to do this, but I would like you to remember that you have that flexibility. Maybe you will be inventors or something like this, right? Those could be better theories than what we have today, because we have a lot of flexibility in defining omega. I said, all we expect from omega is transform phi 0 into psi naught. How to do this? Oh well, that's your imagination, right? Now, let's say, right? So you can play around and maybe come up with better theories we have today. Right now, most of the theories we're using, I wouldn't say all of them, but many theories we're using are based on omega satisfying these conditions, and the class of wave operators that satisfy these three conditions are called the Bloch wave operators, right? So omega is an example of Bloch wave operator. Okay? And I'm sure you've heard the term in one way or another. Well, there it is. So let me comment on these conditions. I commented already a lot about the property 3. How about property 1? This property appears in the literature. Property 1 is often called the intermediate normalization. The same term I've been using so far for wave functions, right? Oh, what is that? Intermediate normalization condition. Okay? Why is it that that's what it means? Well, it's very easy to check it out. What is intermediate normalization as we know it so far? It's an inner product of phi 0 and psi kappa. Okay, what I'm going to do, I'm going to replace psi kappa by our wave operator form of it. So we have omega kappa acting on phi 0, right? Now, from property 1, that's where property 1 enters the consideration. I'm going to stick the projection operator right here. Can I do it? Yes, because p doesn't change phi 0. So I can have it there or not. So I'm going to choose to have it. Okay? It's going to be phi 0, p, omega kappa, phi 0. But we proved in property 1 that p omega is p. Okay? So you end up with phi 0, p, phi 0. But p doesn't change phi 0, so you end up with phi 0 in a product with itself, which is 1. Okay? And in this way, property 1 becomes the operator manifestation of the intermediate normalization condition. Why do I spend so much time talking about it? Well, my daughter would say that I simply talk too much, maybe, all right? But I'll give you another explanation of this phenomenon. That is, when you develop theories, many-body theories, you start with some definitions, you start with wave operators, and you impose conditions on wave operators. Okay? And intermediate normalization, so far to us, was just a practical trick. You remember when I talked about it, I just wanted to avoid the omega square type quantities. Well, that's not everything about it. Intermediate normalization is a key condition to enforce properties such as size extensivity, or the linked nature of many-body expansions, for example. If you abandon intermediate normalization, okay, putting aside some inconvenience, you may end up with theories which are not size extensive in truncated forms. It's not obvious, of course, from what I said so far, right? And I'm not going to probably spend a lot of time talking about it. But I would like you to again register the information. You see papers published, okay, by various developers of theories, many-body theories, that will say, well, let's try to abandon intermediate normalization condition, and let's try to restore size extensivity by some other math trick. And they publish series of papers about that. Okay, so there is there's a research area behind it that says that we should be watching out for this, okay, and then see should we impose it or not. But remembering that abandoning it may actually have consequences for the properties of your theory, okay, and that you would like to maintain. Anyway, right now I would like to sort of take a little digression and tell you a little bit more about the bracketing function, okay? So that you can see this process of finding eigenvalues through curve crossing, which I think is a cool thing, really. All right? All right, so let's do it here. That's not going to be on the exam for sure, don't worry about it, okay? But I think you will enjoy it. Okay, so I would like to sort of have some insight into how f looks like, And I would like to explain to you why we call it a bracketing function. Or we, well, I should say, Leibniz invented the name. Why did he say it? Because I will show you to you now that a pair of values kappa and the value of f at this kappa brackets at least one eigenvalue of the k operator. Okay? In other words, if you choose kappa to be an upper bound of an eigenvalue, then f at the same kappa is a lower bound. Okay? There was a huge effort in the 60s about finding lower bounds of operators. You know, upper bound comes from the variational principle. That's easy. But you know, we don't have a good handle in quantum mechanics about, well, what's the error bar? I mean, how low can it go, right? So actually, bracketing function provides you with a natural mechanism for finding upper and lower bounds. You know, you can maybe publish papers on lower bounds in quantum mechanics, right? Leibniz used to do this. I published one paper in this area. I think this area is pretty much abandoned nowadays, but I would say maybe it's time to return to it because we know a lot more about how to solve the Schrödinger equation today. Okay, so let me explain this to you. So this is f kappa. It is phi0 k plus the k reduced resolvent k phi0. I would like to plot it. Of course, the actual plot depends on what k is, but I would like to sort of sketch it, graphically speaking. You know what you do in calculus if you don't have a graphic calculator, right? You have to sort of look at a few things. You have to look at things like whether my functions are decreasing or increasing, which I can do with techniques of calculus, and I have to look at asymptotes and singularities, right? Those are the three things you typically want to know if you want to plot the function without doing the actual numerical work. All right. So I'm going to draw it. There's an axis of kappa. All right. There's going to be another axis. Let's call it y for now. All right. There's my color. This is my way to think about multimedia. Okay. All right. Let's look at the asymptotes first. Okay. I would like to know how this function behaves when kappa becomes plus or minus infinity. Well, maybe you can tell me what you think. Think for a second and let me know what your thoughts are about that. From the definition. What do you think I should start writing here? Certainly there will be some bracket, but we can certainly do that. The question is, what do I put in the middle?
We're just from k on k.
K. Because this part will go to 0. You remember what the reduced resolver was? It had kappa in the denominator. Right? I erased the definition, but you remember, it was kappa minus k, roughly speaking, to the minus 1. Right? It had kappa in the denominator. So when kappa becomes infinitely large, then simply that expression goes to 0. So reduced resolvent becomes a 0, right? Asymptotically. That's why I don't need to worry about that part. Is this clear to everybody? From the definition of reduced resolvent. So let me draw a little line, maybe in red. That red line here is our asymptote. It's phi0, k, phi0. Okay, that's one thing I know. What else can I try to figure? Well, I don't get that. Well, let's use all language. I would like to know if this function is an increasing or a decreasing function of the parameter kappa. Okay, so let's calculate the first derivative of f with respect to kappa. All right. You know, there is no kappa in k, so that part of the derivative is gone right away. I have to differentiate this part. But kappa is only in the resolvent, so I really have to differentiate the resolvent with respect to kappa. So it's going to be phi0, k, differentiate the reduced resolvent with respect to kappa, k phi0, right? You remember property 5? I proved that the derivative of the reduced resolvent with respect to kappa is minus r squared, right? So I'm going to use it now. I'll write it as property 5 from the previous lecture. Okay? So I end up with minus phi0 k reduced resolvent squared k phi0. But I can rewrite it as minus phi0 k product of two resolvents r kappa times r kappa and then k phi0. Okay? Well, we know that the reduced resolvent is Hermitian, so we know that this is also R kappa dagger. That was, I think, property maybe 1 in our last lecture. K by definition is Hermitian, that's what we said from the very beginning. So what you see here is the inner product of this vector with itself. Can you see it? It's the product of this vector with itself, inner product. Is it clear to all of you? Yes, okay. So that means that, and you know that inner product of a vector with itself is square of the norm of it. So in other words, this is square of the norm of R kappa K acting on phi0. With a minus in front because we had the minus. I'm not even interested in knowing what it is, okay, to be honest with you, right now. I just want to know that the value is negative. Right? The first derivative of the bracketing function is negative, which means that this is a decreasing function of kappa. It decreases as you increase your kappa. Alright? I'm going to go back to our plotting part. Okay? So please copy this. Of course, I'll keep it for a while. Okay? So I would like now to use that information to plot our f. Okay. Can I now move this down? Actually, I can flip. That's right. Okay. So maybe I'll use now blue to start drawing this. Okay. So the function, I'll use white chalk for the function itself. So I start asymptotic, I have to keep going down, right? I know that. Do I go across the whole chart? Across the whole blackboard? No. Because we have singularities. Remember, some values of kappa will cause the resolvent to blow up. Okay? You know, all those eigenvalues, all the kappa values that correspond to eigenvalues of k, q, q. You know, we talked about it. So that means that there are some asymptotes. I don't know where they are, of course. You know, that depends on k. I'm not going to do that. But let's mark them in blue with blue lines. Let's see, that's the first asymptote. Well, let's have another one maybe here. Another one here, and maybe one more. Okay? I don't know how many, of course. You know, I can, well, I'll tell you maybe a little bit later what I know about it. But anyway, let's have that model, right, like this. So I'm going to go down here. Okay? Then I have to go to the other side of the asymptote and have a decreasing function once again. So something like looks like similar to a tangent function, right? With this sort of overall topology of it. Okay? And then, you know, here another branch. And here another branch. A decreasing function. And when you pass the final singularity, you know, you will end up with approaching the asymptote. That's how the bracketing function looks like. Okay? Of course, in real, calculated for a real system, it's not going to be so pretty. Some of these branches will be very narrow. Some will be, there may be many more of them. We did actually calculate bracketing function with Professor Paulus in 1990 or so. We published a paper in Physical Review A at that time, where we computed actually bracketing function with the so-called optimized inner projection technique for a set of systems called cyclic polyenes. You know, the example would be benzene, okay, and then the largest rings like this, okay, and we actually showed what it is. We actually were able to compute lower bounds, we were able to do all kinds of interesting things, but I can tell you it didn't look so pretty. It had the same topology, but the problem was that the density of these branches was huge, especially when you were modeling the metallic regime, where you're approaching the situation where all the orbital levels are degenerate, is the band gap going to zero. When the band gap was going to zero, then the number of these branches was large, so large that you couldn't actually compute anything almost. You could still plot it, but you couldn't do a lot of work. Right? So, but I'm not going to talk about it, I just want to give you a hint that this is all computable actually. It's not like you can't do it, you can do it for real systems now. I want to go back to this issue of finding the, so let's draw a line now, okay? Maybe with this green. So so the white branches are f functions, okay, that's our f kappa. And the green is just the line y equal kappa, right? And I said, all the places where these two cross are eigenvalues of k. Okay, so where do we have these crossing points? Well, there's one here, right? There's another one here. There's another one here. Another one here. So I guess, if we believe, and of course, if you continue, there's another one that I can not showing, you have to continue, right? So it will go over there. with that as this one more time, right? The lowest one is k0. That's k0 when you just read it from the plot. Okay, that would be your value of k0 if your bracketing function is exact. Okay. Now, so now let's talk about this concept of bracketing. Okay. Can I'm erasing this. Can I erase this part? Is it okay if I do? All right. That was a proof that f is a decreasing function. Okay. So what I want to prove now is that if you have a pair of values kappa and f kappa, then they contain at least one eigenvalue. Let's call it Kn. Of course, it depends. If you look at the plot, sometimes kappa is less than the value of f, sometimes it's more. It depends which kappa, right? I mean, f can be a bigger value than kappa or smaller. So so it's either this or f kappa, when this means an interval where the left number has to be always smaller than the right one. Okay? Let's prove it. So the proof of it goes like this. Imagine that I pick up some eigenvalue that is on this plot. Okay? And imagine that I write kappa as this eigenvalue plus some displacement. Just the difference between them. Okay? Well then, I would like to compute, of course we know that Kn's from this plot are fixed points of f. Okay, so we get them simply from this equation. Right? The f at Kn equals Kn. So I'm going to compute now the difference of Kn minus, so the difference of f kappa minus Kn. I know where kappa is. It is displaced by epsilon. I would like to know how f kappa is displaced from Kn. Okay? Well, we know that this is f kappa minus fkn. And do you know the mean value theorem from some calculus, high school probably somewhere, right? You know that if you have a function, if you have an interval a, b, and you have a function, right? Then fb minus fa over b minus a is the derivative of this function at some point c, which is between a and b. Remember that one? Yeah, it's one of the first things one learns in calculus. Okay, so c is simply, so c formally you can write it nicely. It is actually a plus some theta times b minus a, where theta is between 1 and 0. Okay, that's the theorem. Alright, I'm going to use it here. So I have f kappa minus fkn. Okay, so I can write it from this formula. So this is my b, this is my a. Right? So I can write it now as b minus a, which is kappa minus kn, times a derivative of our function, bracketing function, at the point a, which is kn plus theta times kappa minus kn. Right? Where theta is between 0 and 1. This is just a formality. Okay? Well, we can rewrite it using our epsilon quantity. Kappa minus Kn by our definition is epsilon, it's a displacement. And here we have a first derivative of the bracketing function of Kn plus theta epsilon. Okay? Is this clear? It's just a simple application of the mean value theorem. I don't care about what this value really is in reality, I know it's negative. Okay? Remember, this derivative is negative, we proved it already. Okay? So when I go back, I can say that, epsilon, sorry, the difference I should say maybe, f kappa minus Kn has a different sign than epsilon. You agree? Actually, the opposite sign. Yeah. So, in other words, if epsilon is greater than 0, if that displacement is positive, then f kappa minus Kn is negative. And if epsilon is less than 0, then f kappa minus Kn is positive. Okay? Well, let's actually draw it so we see it better. So imagine the first case. What is the first case? I have a kappa line. This is Kn. Epsilon is positive, so my kappa sits to the right of it. Somewhere here. Right? That's a positive epsilon. Now I am saying in that case, F kappa is on the other side of Kn. So it's somewhere here. You see, Kn is between the two. And here the same thing, right? You can see now, so in this case, here epsilon is negative, so you choose kappa to be to the left of Kn, but then F kappa must be to the right. So it's somewhere here. So in either case, the pair of numbers, kappa and F kappa brackets, they are the true eigenvalue of the Hamiltonian, if K is a Hamiltonian, right? You see, we have a beautiful thing. You choose kappa, they'll tell you right away what is the procedure you could use. Choose kappa to be an upper bound. How do you get upper bounds? Variational principle, very easy. Okay? The bread and butter today. CI. You run some CI, and you have your upper bound. Okay? Then you stick that upper bound value, kappa, into the f function, and it returns you a lower bound. And you have the error bars. We rarely have error bars in quantum mechanics when you do calculations, but that's the way to do it. Right? Hasn't been done yet really, well enough so that nobody's using it, I can tell you right now probably, because these lower bounds are produced. We produce them in Joe but we also prove they're poor for the methods we could use at that time. And but this was 1990, we're in 2016. Maybe it's time to come back and get better lower bounds. Poor lower bound, of course, is of no interest today or to anybody because, like poor upper bound. Who cares? It's an upper bound, but it's inactive. Who's going to use it? I think nobody in the experiment will pay attention to such a thing, right? Rightly so, right? But if you get an idea, if you calculate upper bound accurately and lower bound accurately, well then, I think people in the experiment will be interested. Because you will know what is the range, the possible experimental range of these values, right? So, there is a thought in it. Okay, but I tell you now that I want to maybe, before the break, let's say one more thing. With this information, this is all clear, first of all. It's a bit of a digression, but it's really interesting. Now you understand where the name bracketing function comes from. This allows me to prove variational principle, probably the shortest proof of the variational principle that exists. Okay? If we have this bracketing property, then how about if I choose kappa to be minus infinity? Well, certainly, Kn, any eigenvalue, it's a finite number, so it's greater than minus infinity, whatever it is, right? So then I would like to know, so then we know that minus infinity and the value of the bracketing function minus infinity, I write it in this order because this is certainly greater than minus infinity, right? So that pair has to bracket the eigenvalue. Okay? Some eigenvalue, right? So that means that an eigenvalue, right, is greater than, that is obvious already, it's less than the value of the bracketing function at minus infinity. But we already know what is the value of the bracketing function at minus infinity. It's an asymptote with a red line over there. Okay? This is phi0, k, phi0. Now, of course, we don't know which eigenvalue are bracketed here because this is an existence theorem. But if it's a ground state, it's a ground state. If it's not, it's greater or equal than k0. And I'm finished with proving the variational principle because phi0 is an arbitrary function for these considerations. You choose phi0 and you're proving that expectation value of the operator k, Hermitian operator k in phi0 is greater than the lowest eigenvalue. I'm done with the proof of variational principle. I think have you seen a shorter proof than that? I don't think so. I think it always takes half a page at least, right? That's a very short proof, short derivation that an expectation value of the Hermitian operator is greater than the. Of course, it's not greater equal because phi0 is not an eigenstate of k. Remember that we chose phi0 not to be an eigenstate of k. We chose it to be an eigenstate of the unperturbed operator, which is different than k, right? That's right. All right. So I guess now I would like to start start using all these pieces of information to develop perturbation theory. So maybe that's a good time for a break, if you agree. No, we can do it. I talk according to my daughter, so there's a danger for that.
I don't have a feeling for how the quality of the bracketing varies with the actual representation. Because how could the quality
Establish?
You say the quality.
Yeah, so I can do
Your
it.
experience is that the quality is.
Okay, so you know, because you know, in the end, of course, you know, when we look at, yes, it's a very important point. And of course, you know, when we did this, so Levdin and his co-workers were trying, but they were trying systems like H2 plus, you know, some small, very small systems, which are essentially exactly solvable, so you could compare your results with exact solutions. Those were not too bad, in a day, right? I'm talking about late 60s, early 70s, maybe that sort of time period. There were some papers, not only by Levdin, actually, also other people, you know, it's an interesting line of research to find lower bounds, you know, as an alternative to upper bounds. But then when you go to real systems, the situation gets a little bit more complicated because, you know, we can't do what we can do for H2 plus. For H2 plus, it's an analytic problem, right? So we know all the eigenstates and all these things, right? So, you know, it's easier. You're going to go to sort of larger many electron systems. Then you have to use approximate forms of F, which still retain the lower bound property. You know, of course, you have to do it carefully. When you develop these approximations, you have to make sure that you don't suddenly change the basic properties of the bracketing function, but you have to do it approximately. What it means is that you have to even see where the approximations are. They're not in the K, really, because we know K. They are in the resolvent, right? Resolvent. What is the resolvent? I haven't really showed yet the spectral representation of it, but you already know that it's an inverse of kappa minus K, roughly speaking. So it's going to be these perturbative denominators, right? It's going to be differences between the eigenvalues of K and the kappa, right? So that means that you have a sum over states. Okay, of course you don't want to compute sum over states directly because we rarely can get a lot of excited states accurately. Okay, so you have to go with some tricks around that. But in principle, you know, you have to, you know, limit your excited states to some manifold. And with Joe at that time, Paulus, Professor Paulus here, we went, I think, up to triples and quadruples. You know, we use determinants, right? So our fees were determinants, like in MDPT, and then excited determinants were limited to quadruples. And you know, it turns out that that's not good enough for what we call accurate. And now, what I mean by accurate, when we did these calculations, and of course that also depends on the degenerate nature of your system. If your system is really non-degenerate, like a closed shell, where the ground state is isolated, really, you know, like a band gap is big, right? Well, you know, then results were better. We could get, better, by better I mean, you know, we measured accuracy in terms of correlation energy because, you know, in quantum chemistry, we don't really spend a lot of time on Hartree-Fock. Hartree-Fock is easy for us, right? We can get that exactly, pretty much numerically exactly, just by converging with the basis set, right? So it's very fast convergence, you know, it's not a difficult problem at all, right? So, of course, you know, the measure of accuracy was how much of a lower bound for the correlation energy I can get. You know, that's the key question, okay? Assuming that Hartree-Fock is done, right? I want to know what are my upper and lower bounds for correlation energy. So upper bound comes from some CI, for example, right? Well, the lower bound, well, you know, if the band gap was made artificial, actually, very large, then we could actually show that we can get the lower bound within, you know, some few percent, really. So that sounded good, you know, that sounds like very promising. But unfortunately, when you go to more realistic situations or you go toward smaller band gap, okay, then these lower bounds were, you know, really beginning to be look bad, like errors like 100% or more. So we were getting lower bounds, but they were so low that for the practical purpose, okay, I certainly would never dare to go to an experimental person with that kind of number, right? Because that would eventually be a very bad estimate. So of course, then the answer to your question would be, well, I guess that that approximation of the resolvent staying within the manifold after quadruples was not good enough. You have to find a better way. Well, numerically we couldn't at that time, so we sort of stopped. We announced our results. It was interesting, I guess, because it was the first ever calculation. We went up to 22 electron problems. So this was the first ever calculation for a many electron system, right? You could see bracketing functions. You know, you could really see that thing. But also another thing about some bracketing function itself. You know, we used it, of course, to find eigenvalues. You know, these values, of course, they were the lower bounds by the approximate form of the resolvent. Okay, but the thing is that they didn't look so pretty. They looked like really congested branches. Okay, so that was then an issue numerically how to find, because it's, you don't, plotting was even hard in those days, right? Because the density was so high that you have to really zoom it to kind of see what these branches are. Okay, so on the energy scale, right? On the scale of kappa. So this was a little bit tricky. Initially I remember when we thought that initially we thought of it straightforward. We didn't even plot it initially because okay, we know what it is. We don't have to plot it. We just have to start calculating fixed points, right? And we started seeing that when you do fixed points using some iterative procedure, we were jumping, and you can see like, why are these numbers so jumping? And then when we plotted it, we could understand why they are jumping, because you're jumping between branches. In your search for the eigenvalue, you will be jumping between branches because they were so congested, right? So we actually saw, in this paper we have plots that illustrate the problem. So of course there are some problems to overcome. We eventually managed to overcome them, but then the announcement to the world was, well, we're getting lower bounds, but not so accurate yet. Not competitive with what we can do with, say, kappa cluster theory or CI. That's our measure, large scale CI. That's our measure of accuracy, right? If you cannot beat those two, then I think it's not competitive, right? But that doesn't mean that it's not a useful thing to return to, right? It's 2016, we can do this better probably, right? We just did it. Okay. So now, I guess I'll go back to perturbation theory. After all this. So let's see. I guess can I raise now this discussion? This part? Okay. I will still retain the formulas on down the blackboard because they're gonna be useful now. So we are at this point where we would like to develop perturbative expansions. Okay? So far, our K operator, we know from the beginning that we're gonna be writing K as K node plus W. Okay? But I really haven't spent a lot of time doing that, right? I mean, so far I kept my K operator unexpanded. Okay? And we didn't try nuclear, actually, maybe nuclear, maybe it'll work for nuclear, you never know. Nuclear, like maybe double magic with large band gaps, maybe that will work, I don't know. We did it only for electronic problems. Okay, anyway, going back. So we're going to be assuming, we're now back in RSPT, where we're assuming that K is K naught plus W. So as you can easily imagine, the first thing I want to do, I want to see how the wave operator, for which we have a formula now, looks like with this assumption. Okay? That's our very first step. Well, I know it by heart. Let's see. Okay, so what is omega kappa? Well, omega kappa, okay, it's still there. So you have to write it as P plus the reduced resolvent, then K naught plus W instead of K, P. So I have to split it into components. We have resolvent, K naught P plus resolvent, W, P. Okay, well, let's look at the middle term, this one here. I'm going to do a little calculation on the side. So we have R kappa K naught P. Okay, well, let's write it more explicitly. We know what P is. Projection operator P is phi 0, phi 0. And we know that phi 0 is an eigenstate of K naught by definition. That's how we, so far when we talk about these general concepts, I didn't have to make that assumption. Okay, because I didn't talk about K0. But right now, from now on, I'm going to fix phi 0 to be an eigenstate of K0. Really. Okay? So this means that this is kappa 0 times phi 0. And you see that this phi 0 and that phi 0, that's a projection operator. Okay? Kappa 0 is a number, you can stick it outside. So you end up with kappa 0 kappa 0 resolvent and then phi 0, which is P. What is this? Can you tell me? Once again.
0.
0, that's right. For the same reasons we talked about before, because of the Q operator here. So it's a 0. So you can see that the middle part of our expression is 0, meaning that omega kappa is actually a sum of only two terms. P plus R kappa WP. That's the value of omega written in the context of perturbation theory. Okay? Well, that's an important equation, so what I'll do, I'll write it somewhere here. Okay? Let's use this blackboard for the time being as a storage facility. Okay? So we proved now that omega kappa in perturbation theory is P plus resolvent WP. Okay. Well then, let's look at the bracketing function in the context of perturbation theory. Okay? Bracketing function will provide us with eigenvalues. So we have phi 0, I think it's still defined there. The k omega over there on the other blackboard. Okay, so it's going to be k0 plus w instead of k. Then the reduced resolvent. Okay, sorry, not the reduced, but the omega kappa phi 0. Okay, so I'm copying this equation. I'm using this equation. k0 plus w here, omega phi 0. Okay, I have to split it once again. So you end up with phi 0, k0, omega kappa phi 0 plus phi 0 w omega kappa phi 0. Again, we're going to use the fact that phi 0 is an eigenstate of k0. So using turnover rule, here you obtain kappa 0, the corresponding eigenvalue, times phi 0, this way. Right? So I end up with kappa 0 times phi 0 omega kappa phi 0 plus phi 0 w omega kappa phi 0. Okay? What is this one? Can you tell me? 1. That's an intermediate normalization. Striking again, right? Because that's psi kappa, so it's phi 0 psi kappa overlap, right? So in other words, we just demonstrated that f kappa is the unperturbed eigenvalue kappa 0 plus an expectation value of an operator, which I will call tau in analogy to the reaction operator, okay? Phi 0, where our tau with the kappa is defined as P W omega kappa. P I can write in front because P doesn't change phi 0. Let's store this equation too. Okay? So tau kappa is P W omega kappa. But you see, I already know what omega kappa is in perturbation theory. Okay? So I can say that this is PWP plus PW reduced resolvent WP. Okay? So that's another set of important equations. Okay? Okay, so let's maybe summarize and take a little breath right now, right? Okay, look, we are now in a very comfortable place. Psi kappa, our perturbed state, is omega acting on phi 0. Okay? Omega can be split into two parts. The unperturbed part P and the perturbed part resolvent WP. Why do I call it perturbed? Because it is at least first order. W is a measure of perturbation. We'll be simply doing power counting here. Okay? So 1 W is first order. 2 W's, W squared, is second order, and so on. So what you see there is at least 1 W. There's more of it there, of course. But that's at least first order. So that's perturbation. Sometimes in the literature, for this one, people write the term called chi. For example, if you read the book by Lindgren and Morrison about atomic many-body theory, that's a fantastic book actually, by the way, right? And Professor Morrison is nearby, in Louisville, University of Louisville. He also wrote some fantastic textbooks for physicists, for more general forms of physics. Anyway, he's the co-author of it. I think I put it on reserve. Okay, so that's what we have. And if you look at the reaction operator, which really enters now our consideration, so maybe I should add that f kappa is kappa 0 plus an expectation value of the reaction operator. You can see that the reaction operator, so this is a zero order quantity, This is first order clearly. You see, first order right away in front of your eyes. And that's at least second order. 2W's, that's second order. And of course there's more for the resolvent. You see this? We're already beginning to see perturbation theory. If I wanted to stop at second order, I'm done. Because I don't need more to write more. So, you know, everything you know probably by now is already done. Now we're going to do more. We're going to go to higher orders. Okay? Of course, you know, I will not write it, but I think it's obvious to you that at the end we'll fix kappa at k0. Our real wave operator will be then p plus resolvent at k0, wp. Do I need to write it or it's clear to you? Yeah, if you know, because our final kappa will not be some variable kappa, it will be our eigenvalue k0, okay? And then the reaction operator here will be pwp plus pw resolvent at k0, wp. Okay? So now we are at the stage where we would like to develop perturbative expansions. Okay? Now I would like to erase this blackboard if I can. Can I do this now? Everybody? Do you have any questions? I mean, anything that is kind of a little bit unclear, a little bit confusing?
I have to sit down at this first paper.
Yeah, a little bit overwhelming too, yes. I know this because I went through this one day when I was a young person. But I hope it's, you know, you can see that if you really, you know, sure, I understand you may want to reread some of these things, but if you really look at it, it's not really complicated in terms of the types of operation we're doing. That's an advantage of the Levding's approach. It's an operator approach. But you know, operators are not that difficult to manipulate. All you have to remember that they sometimes don't commute. Everything else you could see, I was proving many of these theorems, I used really some elementary manipulation. I wasn't really doing some fancy sort of math tricks, right? I just had to use some operations, of course, knowing where I'm heading with this, right? But that's all. Okay? All right. So now, how do I develop perturbative expansions? Well, you know, from what I said already, we have already some elements of perturbation theory in all this, right? Like for the wave operator, we have the p part, we have a perturbation, but the resolvent is still the resolvent of the full operator, right? Which means that, you know, the k operator, the perturbed one. Which means that what I have to do now, I somehow have to expand it, I have to relate to finish the job. I have to relate our resolvent, okay, which so far was kept in an unexpanded complete form. I have to relate it somehow. That's going to be my statement of related to, okay, to the resolvent called R0, which is the unperturbed resolvent. Resolvent of K0. How would I do this? How do I define it? It's going to be formally the resolvent computed at kappa equal kappa 0. So I'm going to fix kappa at the unperturbed value for the unperturbed operator. So what is R0 then? From our definitions, you remember, it's Q, projector. Then we have in the brackets alpha P, alpha this fictitious parameter, plus Q. Now instead of kappa, I have to put kappa 0. Instead of K, I have to put K0. And then Q, inverted, and Q. That's the formal definition of the reduced resolvent of the unperturbed operator K0. Why do I, you know, why I want it? Because I know it. I know K0, and I know how to get all eigenvalues of K0. Okay, and a little bit later I'll show you the spectral representation with some overstates for this result. Now, of course, you may ask the question, do I know that it exists? You remember there was this problem of singularities. Well, it does exist. Because, remember, in our choices, kappa 0 is a non-degenerate eigenvalue in the p-space. It's an eigenstate of K0 corresponding to phi0. So that operator O can always be inverted in the Q space. Okay? For this choice of kappa 0. Is this clear? Kappa 0 is a non-degenerate eigenstate in the p space. Okay? So I can definitely invert kappa 0 minus K0 in the Q space. Because those denominators that will come out will never be zeros. Okay? So no problem exists. So now we're going to start doing these interesting tricks. Okay, I want to somehow find the relationship between this R and that R. Okay, how do I do this? It's Q alpha P plus Q kappa minus K q to the minus 1q, right? That's the original definition of the reduced resolvent for the k operator. I'm going to use the fact that k can be split. K is k0 plus w, right? So, let me maybe continue here, so I have more space. And now you will see, now we are really approaching the top of the hill. You remember I told you that it's a climb. Now we are like getting close to, I don't know, 8,000 meters, right? Maybe we're still getting this last, this last stretch that you need to push it to get it to the top, right? To place.
8,000 meters is pretty high.
8,000? Yeah, that's Mount Everest, yeah. Well, I think we agree that this is a high-level class, right? So let's talk about Mount Everest type problems here. Why not? Right? Let's be.
I assume we're going to get oxygen.
Yeah, but you are great people. You can do it without oxygen. You're like some of those few people who managed to do it without it, right? Okay. Okay. Next time I'll order some oxygen. All right. Okay. Anyway, going back. So what is then our kappa? Well, it is q alpha p. I'm going to also do some splitting, okay, of this term kappa minus k. I will write kappa is kappa minus kappa 0 plus kappa 0. So addition through subtraction, simple trick. Okay, that's a kappa. And for k, I'll write k naught plus w. So it's going to be minus k0 minus w. Okay, and then q to the minus 1 and q. Now you can clearly see there are two kinds of pieces in this expression. Maybe I'll mark them here. So there is a piece which is a zero order piece. Okay, this one here. That's kappa 0 minus k0 that you see in the reduced resolvent of the unperturbed problem. And there are these other pieces. So I'll split this expression accordingly. I'll write it as q alpha p plus q kappa 0 minus k0 q. Okay. And then minus q, all those other pieces are called them w kappa prime. And I'll define what it is in a second. Q. So, what is w kappa prime? You can see what it is. Those are all the things in blue here. It's w minus kappa minus kappa 0. Okay, if you can see it through back substitution. If I put this back, I will end up with q, w, q, that's here, with a negative, and then I will have this minus cancelling that minus, so it's going to be kappa minus kappa 0 with a plus. So that's exactly what we have here, alright? And now I'm going to use what you have in your homework, okay, what you need to do in your homework. Okay, let's call this part the A operator, okay? So let me actually define it, right? So A will be alpha p plus q kappa 0 minus k0 q. And let's call this one the B operator. Okay, so my B then is q w kappa prime q. And in your homework, you are asked to prove how to deal with a minus b to the minus 1 in various ways. I gave you 5 ways of doing it. Okay? I'm going to choose one of them. A minus b to the minus 1 can be written as a to the minus 1 plus a to the minus 1 b a minus b to the minus 1. Right? And that's in your homework. It's easy to prove. Right? I think I gave you all the hints to need. Well, it's so simple, but not much of a hint is needed here. But anyway, I think you're going to prove it yourself. And then see it in the solution key eventually. Okay, so I have this situation. You can see what I have there is a minus b to the minus 1. So I am in this regime. So what do I then get? Reduced resolvent of the full operator equals, well, there's a q in front. Then you have to take a to the minus 1. So you have to take the a piece, which is alpha p plus q kappa 0 minus k0 q to the minus 1 times q. That's the a to the minus, that's what comes from the a to the minus 1 part. Okay? Then according to this recipe, I have to continue and I have to now write plus a to the minus 1, but remember there are q's on both sides of our equation, so we have q alpha p maybe I'll write it below, Q alpha P plus Q kappa 0 minus K0 Q to the minus 1, okay? That's A to the minus 1. Then I have to stick the B. Well, B is Q W kappa prime Q, all right? Maybe I'll keep marking these things. So this is A to the minus 1. This is A to the minus 1. This is B. And then I have to do A minus B. But A minus B is, is the whole thing. What was in the original resolvent, okay? So for the A minus B, I will have alpha P plus Q kappa minus K Q to the minus 1. That's A minus B to the minus 1. The original square bracket expression. Okay? On the vertical. You see it there? A minus B. That's the original. That's what we have there. Okay? And then of course you have to remember that I have the Q. In the resolvent I have Q on the right, so I have to stick that Q in there. Okay? So this part here, all of this is, well, up to here, I should say, is A minus B to the minus 1. So I use our recipe. Okay? All I have to do now is to read what I see. Maybe you can tell me. What do you see when I start writing these terms? What do you think the first term is? What is the very first term? This one.
R0.
That's R0, exactly. So you have R0, the unperturbed resolvent. Then what else should I say? What is, maybe I'll put it in blue. This part. What is this one?
Something's close.
R0 again. It's R0. Same R0 as before, right? So I have R0. Then I have W, this new quantity W prime. And then, what is this one?
R, the full result.
That's the full resolvent, right? Exactly, you see? It's not that scary. So I found a procedure of iterating the resolvent. Of course, you see, I'm sure, Mark, you saw it in your Green's function type considerations. The G equals G naught and then the perturbed part. So this is a well-known, of course, formula, but we're using it here in the context of resolvents. Okay? Well, so now the final thing for today, I'm going to now use this to iterate the resolvent. Okay? So what do we get? R0, R kappa equals R0 plus R0 W kappa prime. Now I replace this resolvent by our formula, okay? Which is R0 plus R0 W kappa prime R kappa, right? I can then split it, and I obtain R0 plus R0 W kappa prime times R0 plus, and then I have R0W, so I have it in a square. So we have R0 W kappa prime with a square, and the resolvent. Okay? I can of course continue. I can replace the resolvent here, again by what's in the box. Well, let's do it one more time then. Because I think you probably already are seeing what's coming out. But I guess I'll do one more iteration. So if I continue this iterative process, I have R0 as the leading term, no surprise here. Then we have R0 W kappa prime times R0, that's the first term. Then we have R0 W kappa prime square, and then instead of the reduced resolvent, I have to write again R0 plus R0 W kappa prime R. Okay? So when I continue, then I end up with R0 plus R0 W kappa prime times R0 plus R0 W kappa prime. You see you have a square here. Okay? And then you have R0, so that's going to be square R0. And then the next term will give us R0 W kappa prime. You have a square here, you have one more here. Well, that's a cube of it. And then the resolvent. You know, you see where this is heading? It's heading to our power series expansion, where R0 W prime is your key quantity that you're iterating. So we now proved an extremely important theorem, that R kappa is R0 plus a sum over n from 1 to infinity R0 W kappa prime to the n acting on R0. You see it all the time. It's some power of R0 W prime and R0 in front. Of course, assuming that this converges, which is a separate question. Alright? But you can also see that I can formally absorb the leading term into the summation, because if you put n equals 0 here, you know, by definition, the zeroth power of anything is the unit operator here. Alright? So in other words, I can rewrite this in a beautiful form. Okay? Now we are approaching that mountain. So we're now close to the top. R kappa is a sum over n. Maybe I should say R kappa of the pull operator, just to make sure that we remember it. Is a sum over n equals 0 to infinity. R0 W kappa prime to the n R0. This is our perturbative expansion that will be a basis of our considerations. Okay? So the final thing I'm going to write is what I can draw from our considerations. So with this form, you can see I can stick it back into the definitions of omega and tau. I can replace these r's by their perturbative forms. And what do we get? Then our wave operator omega kappa is P plus a sum over n from 0 to infinity R0 W kappa prime to the n R0. Okay, that's the resolvent. Then you have W and the P. Okay, that's the perturbative expansion of the wave operator. Okay? When you apply this wave operator to phi0, that's going to be the expansion of the wave function. You just have to replace kappa by k0. What about the reaction operator? Okay, we still have it, sorry, for the bracketing, yeah, for the reaction operator, that's okay, right? It is, oh, I didn't store it here, I guess.
Yeah, it's right there.
Is it, where is it?
Second line.
Oh, yes, okay. Oh, that's called blindness, all right? This is a way to communicate that that's end of the lecture. Yeah, one gets blinded then. So it's PWP plus P W. Then I have to replace the resolvent. So you can see what I have to do. I have the summation over n from 0 to infinity. Okay, I have P W, and then I have R0 W kappa prime to the n. Okay, that's the resolvent part. Then W and P. Okay, and that's the expansion of the reaction operator, which means that once you bracket it up with, with phi0, that's your energy expansion, the eigenvalue expansion, right? Because we compute an eigenvalue by shifting kappa 0 with the expectation value of this. So this is going. I have to stop here. So please note what we have. We accomplished a massively important thing. If I ask you a question, what's the first order? You know it right away. That's first order already. Okay? That's higher orders because what is W count? What is W? W is already a first order or higher order quantity. Remember the W prime? I don't know if I stored it, but I write it again. W kappa prime is W minus, remember that was the shift. This is unperturbed. Kappa is perturbed. So the difference is at least first order. So it's first order or higher. Because in our definition of the orders, W is the count power, is the counting parameter. Okay? So that's at least first order because this is zeroth order, you're subtracting from kappa, so that's at least first order. Then this first order by definition. Okay, which means that our W prime is first order, at least first order. Okay, so when you go back, that means that this is at least first order. So if you want to know the first order only, that's this one, WP. So you already know how it looks like. P, it's got, sorry, so actually this is actually what I was talking about this one. So yeah, so this is then first order. So if it's n greater or equal 1, okay, it's first order higher, that means that WP, R0 WP is your first order wave operator, or first order wave function, okay? And you can see for the energy, this is first order, this is at least second order, because even if n is 0 here, that's P, W, and then I think I missed R0, didn't I? That was R0, right? From the result. So it's R0, please correct. R0 WP, right? So as I said, one W, another W, that's second order, and that is at least first order. If so for n equals 0, this is actually 0 order here. So that means that we have a natural decomposition. Kappa 0 is a 0 order. This is first order. That's second order and higher. Okay. So next time we'll simply resume from here. We'll develop perturbative expansions. We'll write down formulas for the first few orders. Okay, and then we'll start going back to MBPT. All right. Okay. Make sure please that you have that result. Thank you. See you on Monday.